Hello everyone, welcome back to the course Vector Calculus and Complex Analysis. Myself Dr. N.CH.Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. Today, I am going to introduce a concept called conformal mapping. And coming to the overview of today's presentation, today the introduction to the conformal mapping and the applications of conformal mapping and some definitions and some transformations we are going to discuss. And coming to the introduction part, a conformal mapping, that means the same form or shape, is an important technique used in complex analysis and which has many applications in different physical situations. And also, if the function is harmonic, and that means what is the definition of harmonic function? If it satisfies Laplace equation, then it is said to be harmonic. So if the function is harmonic, then the transformation of such functions via conformal mapping is also harmonic. So if the function is harmonic and we are using the conformal transformation, then the transformation is also harmonic. So equations pertaining to any field that can be represented by a potential function, that means all conservative field, in all conservative fields, can be solved via conformal mapping. So using this topic or conformal mapping technique, we can solve the equations pertaining to any field related to potential function. And if the physical problem can be represented by complex functions, but the geometric structure is not available or not convenient, then it is better to use this conformal mapping. So mapping, it can be transformed to a problem with much more convenient geometry. So for that we use the conformal mapping. So a conformal map is a function which preserves the angles, and a conformal map preserves both angles and shape of infinitesimal small figures, but not necessarily their size. So mainly the conformal mapping preserves the angles. So here what will happen? What is the mapping first? Mapping means if I write w equal to f of z, it transforms a point from z plane to a point in the w plane. This is called a mapping. And conformal mapping is a particular mapping which satisfies the definition that preserves the angles. So today I am going to discuss about the conformal mapping, the necessary definitions, some examples and some transformations. And coming to the application part, a large number of problems arising in fluid mechanics, electrostatistics, heat conduction, we can apply this conformal mapping technique. And not only this, many other physical situations can be mathematically formulated in terms of Laplace equation, and also we employ this conformal mapping technique to solve such physical situations. Now coming to the definitions, mapping or transformation. Just now I told w equal to f of z, where z is x plus iy. So a point in z plane is transformed to a point in w plane. This particular transformation w equal to f of z is called a mapping or a transformation. The corresponding points w in the w plane are called images of the points. That is as usual definition of a function or a mapping. For every point of z plane, there corresponds one and only one point in the w plane, then the correspondence is said to be one-to-one correspondence or one-to-one mapping. This is the introductory definition. Now coming to this conformal mapping, let us consider a transformation w equal to f of z. And we know that f of z can be in the form of a complex variable. So here u complex function u of x comma y plus I into v of x comma y. Consider this transformation and consider a point p x naught y naught in the z plane, which is mapped to p dash of u naught v naught of w plane. So the point p x naught y naught is mapped to p dash of u0, v0. Now let us consider two curves C1 and C2 at which intersect at a point P x0, y0 in the W plane, which are mapped into C1 dash and C2 dash, which intersect at P dash, the point P dash, through this mapping. So using this transformation, we are transforming or we are mapping two curves C1, C2 in W plane, in Z plane, to two curves C1 dash and C2 dash in W plane. Now, if the transformation is such that the angle between C1 and C2 at the point x0, y0 is equal to the angle between C1 dash and C2 dash at u0, v0. That means, if the angle between these two curves at the point x0, y0 and the angle between C1 dash and C2 dash at the point u0, v0 is the same, then the mapping is said to be conformal mapping. And if the transformation preserves the magnitude but not necessarily same, then it is called isogonal transformation. So here it preserves magnitude but necessarily preserves the magnitude but not necessarily same, then it is called isogonal. Now here we have Z plane and W plane and a point P x0, y0 in Z plane, P dash at x0, u0, v0 in W plane, and we have two curves C1 and C2 and C1 dash and C2 dash in W plane. So two curves C1 and C2 are in Z plane and C1 dash and C2 dash are in W plane. Now for example, so this is x axis, y axis, origin, and this is the curve C1, C2, and let us consider this angle between these two curves is alpha. Then coming to the W plane, so here this is u, v, and this is the point P dash, and here this is the point P. Now this curve is C1 dash, C2 dash, and let us consider this angle be alpha dash. So the angle between the two curves C1 and C2 is alpha, and the angle between C1 dash and C2 dash in W plane is alpha dash. So if alpha equal to alpha dash, then the mapping is said to be W equal to f of z is said to be conformal mapping. So that means it preserves the angle. So both the angles must be the same. A conformal mapping requires that the derivative of the function be non-zero at every point. That means if you we have the function w equal to f of z, so the function f of z, find its derivative f dash z. This f dash z must not be 0 for all z in the z plane. So if the derivative is not equal to 0, then the mapping is said to be conformal mapping. For example, if the derivative is 0 or infinity cannot be determined at some point z equal to z1, let us suppose, then this z1 is said to be a critical point. So critical point, the points where f dash z is 0 or infinity are called critical points. Ordinary point means at which the point at which the derivative is a non-zero. So f dash z not equal to 0 are called ordinary points, and f dash z is 0 or infinity are called critical points. For example, consider a function f of z equal to z square. Now f of z equal to z square. What is its derivative f dash z? 2z. Now f dash z is 0 at z equal to 0. If f dash z is 0, 2z is 0, that means z equal to 0. So z equal to 0 is a critical point. Similarly, another example, cos z. What is its derivative? F dash z is minus sin z. So f dash z equal to 0 implies minus sin z is 0. So sin z is 0. Sin, when will be the function? Sin function vanishes, becomes 0. So sin z equal to 0. That implies z can be n pi. So sin becomes 0 for the angle n pi. where n belongs to z, the set of integers. So z equal to, you can take 0, plus or minus 1, plus or minus 2, and so on. So for all these values, sine function vanishes. Hence, these are the critical points. So what are the critical points? The points at which the derivative vanishes, or the derivative becomes 0. Now, coming to the standard transformations. There are two standard transformations called translation and expansion or contraction and rotation. Expansion or contraction and rotation. That means magnification. This comes under magnification. Now, coming to the first one, translation. Let us consider a transformation of the form W equal to Z plus C. Let us consider this transformation. Now we have, what is Z? X plus Iy. And here this C is a complex constant. So Z equal to X plus Iy, and you can take C as C1 plus IC2 because it's a complex constant. Now let us use these two. Let us use these two in this transformation. So W equal to X plus Iy plus, this is Z, plus C, C1 plus IC2. Now by simplifying, let us write the real part X plus C1 first, plus I into the imaginary part Y plus C2. So that means this transformation transforms a point xy in Z plane to a point X plus C1 comma Y plus C2 in W plane. So here both are similar. Here we have X, here X plus C1, Y, Y plus C2. That means here this transformation transforms a figure of the same figure in Z plane to the W plane of the same size and shape. So here the transformation W equal to Z plus C transforms a figure in Z plane to the W plane of a figure having the same size and same shape. In general, circles will be transformed to again circles in W plane. So this comes under translation. Now coming to the second one, expansion or contraction. Expansion or contraction and rotation. So here let us consider the transformation W equal to Cz, where C is a complex constant. Complex constant. Now let us consider Z as R e power I theta in polar form, R e power I theta, and C as some beta e power I alpha. Then using this transformation, using these two in the transformation W equal to Cz, we get W equal to C is beta e power I alpha multiplied by R e power I theta. And here I can write this beta R and e power I alpha into e power I theta, which is e power I into alpha plus theta. Now I will use a new notation here, where this beta R is denoted by capital R and the angle alpha plus theta is some phi. Now using this transformation, what happens here? Particularly we are discussing about expansion or contraction and rotation. So when it will be the expansion comes or contraction comes and rotation comes. Here we have this C equal to beta e power I alpha. So the expansion comes when this mod C is less than 1 and contraction comes when 0 less than mod C less than 1 and with a radius beta equal to mod C. And what about this rotation? Rotation comes where it will be rotated with an angle alpha equal to mod C. So this under this transformation W equal to Cz, the expansion or contraction and rotation happens. So these two are called the standard transformations: translation and expansion, contraction or rotation. So today I have introduced a new concept called conformal mapping. Everybody knows about a mapping. For example, if I write y equal to f of x, it is a mapping or a transformation which transforms each x value to y. Similarly, w equal to f of z in complex variables. So this transformation or a mapping is said to be conformal mapping if the angles are preserved. That means angle between the two curves in w z plane and the angles between the two curves which are transformed to w plane, both must be the same, equal. Or we can say, if the derivative of f dash z is not equal to 0, then the function is said to be conformal at that point z. So in the next session, we will continue the same topic and we will discuss about some other transformations or mappings. Thank you very much.